All right, let's get started. And currently we are discussing about graph database systems, which are systems that are specialized for processing graphs data, which is represented as nodes and connection between those nodes. The last time we have been discussing about one specific representative, which is the Neo4j system. We have looked a little bit at the Cypher query language, which allows you to create and query graphs. This is one of the last things that we have seen last time. I asked you to create a little graph which represents the situation that is described here. In the following, we're gonna see a couple of more features of that query language and a few more examples. And afterwards, we're gonna start discussing about a distributed graph processing. All right, so we have seen last time how we can represent this example as a graph. After creating a graph, of course, we also want to query it and find interesting patterns and subgraphs within it. So the way you query those graphs, you typically use some kind of a matching expression, and then you use the return clause in order to indicate to the system which parts of the pattern that you are matching it should return as the query result. So here in this example, we are looking for a student named Mark, which has a friends with connection to another student assigned to the variable s. And ultimately, we're interested in s, so we are returning this as query result. So this query essentially looks for the friends of student Mark. You can vary that. For instance, here, if we use this little asterisk there in the relation, it means that we can essentially chain those relations. So in this query, we are looking for friends of Mark, for friends of their friends, for friends of their friends, and so on. So we are essentially looking for pairs in that graph. You can also limit the number of steps that you are willing to make. For instance, with this notation, anyone has an idea what this probably means? Okay, one proposition is a student friends at 3 edges away from Mark. Yeah, that would be a possibility. So so here definitely we are accepting multiple friend relationships in between the nodes that we are interested in. And here basically we are willing to accept between 0 and 2 connections. So that means this would include Mark himself, because of we are accepting 0 connections too, and everyone who is friends with Marks and all the friends of the friends of Mark. So you can tune how many steps you're willing to make in that graph. We can also do aggregation. For instance, we can look for the number of occurrences of a pattern using the count clause, and this syntax is similar to SQL, as you see. And you can, of course, look for more complex patterns by combining the things that we have seen. So here we are looking, for instance, for there's a student S1, which has to be friends with a student S2. S1 should be enrolled in a course C. S2 should also be enrolled in course C. And we have some restrictions on the name of the first student and on the name of the course, the syntax here again is very close to SQL. Again, you have a where clause in which you can specify conditions for filtering those patterns. And here we have the student name must be in the list Mark or Maria. And the course name should not be equal to CS4320. So altogether here, we're looking for students who are friends of Mark and Maria and have one course in common that they're both enrolled in, but that course cannot be CS4320. And in the end, we are returning S2, so we are interested in the other student. All right. So, and there's one little question for the path length of 0 to 2. So here we essentially, between the first node and the second node, we can have between 0 and 2 edges. So if it is 0 edges, then that's the node itself. If it is 1 edge, then basically you have 1 connecting edge. You can have 2 connecting edges, and those are the possibilities that we want to consider in this query. So from the start student, all the students that can be reached with at most 2 steps. And how many students are in the result of the query, that depends on the content of the graph. And if you want a specific path length, then you can just make the lower bound equal to the upper bound. We have seen this notation. We have the lower bound dot dot and then the upper bound. And if both of them are the same, then you're looking for a path with one specific length. Does it make sense? Awesome. Okay, great questions. And please always feel free to ask questions. And now I have a little exercise for you in which I want you to retrieve courses taken by at least one student who also takes CS4320. So think a little bit about how you would formulate this using the Cypher query language. And then in a minute, we're gonna see a solution. And if there's any questions about the query language, please don't hesitate to ask them. Right? So let's see how we can actually do that. The question was to retrieve courses that are taken by at least one student who is also taking CS4320. So in this query, we have multiple entities appearing. First of all, we have the course that we are looking for. Then we have the student who is taking the course. And then we have CS4320, which is another course, and it has to be taken by the same student. So here we somehow have connections between three nodes in the graph. So we want to formulate a matching expression where we have, first of all, the CS4320 course, which should be of type course, and the name should be CS4320. Then we want this connected via the enrollment relationship to the student taking it. And that student should also be in an enrolled relationship with the other course that we are interested in. And finally, we're interested in this other course. So, right. Yeah. So here currently I don't have any content in the graph, but this is one way of solving, of translating this description on the slide into a Cypher query. All right. Okay, there's another question about an alternative representation. Okay. All right. Yeah, so here basically we can also put some of the conditions that are now merged into the node references. We can also put them into the where clause, for instance. We also have some directed edges here in the query, while I used undirected edges in my query, but that should be fine as long as you know into which direction the edges point to. And otherwise, yeah, the structure seems to be the same in this query. Yes, there's one slight syntax typo, but yes, the structure, yes, that is also a possibility. Okay, and here's the question, how we know when to use match and when to use where for a given condition. And frankly, for many conditions, you can either put it into the match clause or you can put it into the where clause. It's like with SQL queries, there's typically many ways of writing the same query, and ultimately it's a matter of personal preferences, which one of them you prefer. So there's no principled reason to put certain things rather into the match or into the where clause. Ultimately, it depends on your preferences. All right. Good. We're going to see a few more examples towards the end of the lecture. Now, I'm quickly going to tell you a little bit more about the internals of the system. And by the way, now we have solved some more complex problems. Initially, we started with an example graph representing the metro of New York City, and we wanted to find a path between two specific stations. And now with the features that we have seen, this would become a relatively short query. We are simply looking for paths from the first station to the second station. And if we use this asterisk in the connection, then we are automatically looking for paths of arbitrary length, which was not as convenient to represent in SQL. Now, the Neo4j system uses a specialized data layout, which makes it particularly efficient to traverse graphs. So to be precise, it has one data layout that is used for storing data on hard disk and one that is used to store data in main memory. And here I'm describing the in-memory layout where we are storing for each node the labels and properties and also a list of the outgoing edges. Also, we store the edges separately with the labels and properties and with references to the nodes that are involved in those edges. We might also have indexes that allow us to very quickly identify nodes with specific properties or with specific labels. If a query comes in, then it is translated into a query plan, which is composed of standard operators. Many of them are essentially known from SQL processing. You have operators for filtering, for projection, and so on. You have also a few graph-specific operators. For instance, if you want to find shortest paths between certain points in your graph, then there is some specialized algorithms available. And in order to find the best query plan for your input query, like the relational database management systems that we have seen here, we also use cost-based optimization. We can also process transactions. By default, Neo4j supports read-committed isolation, but you can get higher isolation levels if you manually acquire logs. There's commands for doing that. And also, we have mechanisms to allow recovery by writing log entries to persistent storage. So all things considered, you can have ACID transaction processing with this system. So this is a very high-level overview of the system. Now, let's make a few more examples, perhaps this time for a different database. And read committed isolation, that's one of those isolation levels that we also use for SQL. And essentially means you can only see those things which have been, those values which have been written by committed transactions. But there's some other anomalies that it still allows. For instance, you might not have repeatable reads if you repeatedly reading values in the same transaction that somewhere in between are changed by a different transaction that commits. All right, so now a few more examples with a little bit more complex database, which contains a graph representing movies and the people who directed them or played within them. So for instance, here, if I want to find out persons who have played in specific movies, I can do this with a match expression. Perhaps here, I first want to specify a specific movie. I could, for instance, use The Matrix, science fiction movie from a while ago. And now I want to find people who acted in that movie. And now I want to return both the movie and the person. I have to, huh? And that explains why I'm not seeing any results here. I used a property named name, but I should have used a property named title. And now I think it should work. All right, now I'm getting a list of the people who played in the matrix as a graph representation. I can also expand on that. Perhaps I'm interested in people who have played in the matrix, but also in the follow-up movie, which I believe was called The Matrix Reloaded. So let's extend the query here. And now we have another movie with title The Matrix Reloaded. Now here we are seeing the set of actors who have played in both movies together with the connections between the actors and the movies. All of them are presented as nodes in this graph over here. Perhaps one more example, not specific to this movie. Perhaps I'm interested in cases where a director at the same time played in his or her own movie. I can also represent that as a query here. So I'm looking for somebody, for some person who has directed a specific movie. And at the same time, we want that person to have played, to have acted in this movie. So here I'm using the same variable name P twice, which means that they have to be assigned to the same node in the graph. And I have one connection between the person and the movie of type directed, and another connection of type acted in. So here I'm looking for the people who have played in their own movies, basically. And here I want to return everything, so I can just use this asterisk here. All right, and here I'm getting a couple of matches. There seems to be one movie by Clint Eastwood, for instance, and another one by Tom Hanks and Danny DeVito. In all of those cases, I have this pattern that I was looking for, which essentially contains two nodes, the movie and the person, and two connections between them, the directed and the acted in connection. All right. And what I can also do, I told you a little bit about the internals of the system. If you ever want to find out how a database management system processes queries, then a good guess is to just prefix your query with the explain command that works in Postgres, that also works here. So if I prefix that with the explain command, then it should give me a description of the query plan. So the query plan is also represented as a little graph here. So we read it from top to the bottom. I'm gonna make that a little bit larger here. And as you see, the plan starts by a node by label scan. So here I'm essentially using an index which gives me nodes for one specific label, which in this case is the movie. So here the system decided to first search for the corresponding movie nodes. Then after finding the movies, I'm trying to connect them to a person by the directed relationship. So here in the expand operation, I'm going along edges pointing from the movie to a person. And here I'm gonna essentially look for persons that have directed the movie. For the moment, P is just a variable, so I'm looking for directed relationships pointing to any kind of node. In the next step in the filter operation, I'm narrowing it down to persons, even though in this case, that might not necessary because it's typically persons who direct movies. Nevertheless, here we are filtering it down to nodes with the label person. Then we make sure that there also exists a connection of type acted in between that same person and movie that we're currently analyzing. And finally, we produce the result set. You also see that there's a couple of estimates over here. For each step, the system tries to estimate how many rows we are getting, and that is very similar to what relational database management systems do. We also try to estimate what is the output size for each operation, which is helpful in order to identify the cheapest query plan. And here you see we have those estimates. They are close, but not entirely precise. In the end, we got actually 3 matches here. The number of estimated matches is only 2. So as in relational database management systems, those are just the estimates, and every once in a while, they are off the true values. All right. I'm quickly looking whether there is a question. Okay, that is a great question. How does it come that the diagram shows directed arrows while I was using undirected arrows in my query? Let me quickly illustrate this in more detail. That is a great point. So here in this query over here, we can see directed arrows between the movies and the person. But the query that I used here, you can see the query again. I used undirected edges in my query. So those undirected edges essentially mean that I'm interested in directions into both directions. Internally in Neo4j, there are no undirected edges, but they always have one direction. So if I search for undirected edges, it essentially means that I'm interested in edges in both directions. So that is essentially a more general than if I had specified a specific direction for the connection. So here, the directed edges, they match my query because they essentially specialize the undirected edges that I'm referencing in the query. But that is a very good observation. Yes. All right. Any more questions on those examples before we switch to distributed graph processing? Okay, and here's a question about why the cost estimates are in rows if the data is stored as nodes. Well, I mean, in a way, what each row symbolizes here is essentially one connection, one match for the patterns that we're currently considering. So you could also call this a graph fragment, for instance. Neo4j actually gives you the possibility to also represent the results as tables. So I guess that might be one of the reasons why they chose this, this term. But I could also imagine choosing different terms for that. The semantics is essentially that we have one of those graph fragments that matches some part of the pattern that we specified here. All right. So if there's no questions for the moment, then I'm going to continue with the next subtopic, which is about distributed graph processing. So We are still discussing about graphs, but now we are discussing about particularly large graphs. The reading list includes those two papers you see here. One paper from 2010 introducing a system called Pregel that we will discuss about in the following. That was by Google members. And then one later paper by Facebook employees in 2015 about a system that was significantly inspired by Pregel. Now, the motivation for those systems are particularly large graphs, where we would typically not be able to store them and process them on one single machine. For instance, Google is interested in mining the entire web, and you can represent the web as one big graph. Facebook is interested in mining their social network data, which also is natural to represent as a graph. And in those cases, you typically want to do the processing in a cluster of machines. Now, one famous example of an algorithm that must run on a large graph, it's the PageRank algorithm. That is used by Google in order to rank your search results. So this algorithm that we will see in a little bit more detail in the following operates on a graph representation of the web. Here, nodes represent websites and edges represent links between those websites. And the goal of this algorithm is essentially to associate the nodes to a PageRank value, where higher PageRank value means that this page probably should be ranked higher in your search results. The PageRank algorithm is based on the random surfer model. And here we're talking about a randomized web surfer, which essentially starts from some random website and then randomly clicks on any link leading away from the current page. And it selects among the outgoing links with a uniform random distribution. If the surfer ends up in a dead end, meaning a website which has no outgoing links, then it selects a site to jump to randomly among all sites on the entire web. Optionally, as an extension, we can also allow the random surfer to not follow outgoing links, even if there are some, but instead with a certain probability alpha to select again some random page on the entire web. And when following this model, then the random surfer will come by websites every once in a while. And the idea is that perhaps the important websites that more links are leading to, they are visited more frequently. So the PageRank is essentially proportional to the probability to be at one specific site at any specific instant in time. So essentially, it's the percentage of your time that you will spend on that site when following the random surfer model. Now, this is a little example over here to illustrate the PageRank algorithm. So here we have websites represented as nodes, those blue circles, and we have links represented as those arrows between the circles. And in those circles, you see the PageRank value here scaled to a total value of 100 if you add up all of that. And as you see here, PageRank is not evenly distributed, but those nodes on the top of the slide, they have most of the PageRank, and that is because they have many links pointing toward them. And also the node on the top of the slide and on the right-hand side might not have that many links pointing into it, but it has a link, an incoming link from the node in the middle with 38.4 PageRank. So that's a very central node, and having a link from a node like that, that is particularly useful. All right, so this is a little example. I told you before that optionally we can allow the random surfer to jump to a random page with a certain probability alpha. When looking at this graph, can anyone tell me whether we have use this option in this case. In order to generate the PageRank values here, did we allow the random surfer to jump to randomly selected pages with a certain probability? Does anyone see an indication which version we were using here? Very good, very good. Yes, exactly. So here, as your colleague is pointing out, we have nodes without any incoming links, for instance, at the bottom of the slide, to the left and also to the right. And those nodes, they nevertheless have a non-zero PageRank, which means that the only way to reach them is by random jumps. So since that was possible, we must have enabled the option to do random jumps. Okay, very good. And the way to calculate the PageRank, there's multiple ways, but you can use an iterative algorithm where you initially assign a PageRank of 1 divided by the number of nodes, meaning the number of websites, to each of the websites. So this is because the random surfer initially selects the start website with a uniform random distribution. And then in each iteration, we redistribute the PageRank. The PageRank is essentially flowing along the outgoing links from a page, and each page partitions the PageRank equally among all outgoing links. And then in the next iteration, the new PageRank of a website is the sum of the PageRank packages distributed over all incoming links. And we can iterate that a couple of times until it finally converges, and the result of the convergence that represents the probability that the random surfer spends time on a specific site. Now, this is an illustration for how we update the PageRank values for each node in this iterative algorithm. So here we see PageRank values at iteration I and at iteration I+1. And here we have 2 nodes, one with current PageRank 90 in iteration I and one with current PageRank 10. And they distribute their PageRank equally across all of the outgoing edges. And for instance, the node on the bottom on the left has a PageRank value of 10, and it has 2 outgoing links. So it will distribute a value of 5 over each of those outgoing links. And the node on the left on top of the slide has a current PageRank value of 90 and 3 outgoing links. So it will distribute a PageRank value of 30 across each of those outgoing links. And now in the next iteration, the node on top gets 30 from the first node and a 5 from the second node. So by summing that up, we get a new PageRank value of 35. And the node on the bottom only receives PageRank from the node on top on the left. So we have a new PageRank value of 30 in iteration I+1. So this is the principle how I continuously update the PageRank values of the nodes in each iteration. Now, Pregel is a system which can do computations like that on very large graphs that are processed by large clusters of machines. It was described in 2010 by a paper by Google, and PageRank was one of the use cases for that paper. So we generally partition our graph into smaller parts that are managed by specific worker machines, and then they can do iterative processing on those partitions in parallel. Now, the Pregel computation model works as described here. So the computation is divided into multiple iterations, which are also called super steps in this system. In each iteration, we invoke the compute function for each node in our graph. So we do some node-specific computation, and the way you specialize this system to solve one specific problem is by overriding the implementation of the compute function. So that's a little bit of a more low-level interface than some of the other systems that we have seen so far. The compute function takes as input messages sent to one specific vertex, aka node, in the previous iteration, triggered when processing the compute function for other nodes in the graph. And also, while processing the compute function, a node might generate outgoing messages that will be delivered in the next iteration. The entire computation ends once all the nodes vote to halt, meaning that they don't have any more work to do. And in that case, the system returns the final result. Now, this is an illustration of how the computation works from the perspective of one specific node here in the middle. And the node in iteration I will process messages sent to it in iteration I-1 from other nodes. And it will also produce outgoing messages for other nodes that will be delivered in the next iteration. And beyond the receiving and sending messages, we also have this flag indicating whether the node wants to hold the computation, which it does if all the nodes have voted to hold. For instance, here we have had the example of the web graph. This is, of course, a small graph. In reality, it would be way too large to represent. We would divide this graph into partitions, where each partition is defined by a subset of nodes. You can try to optimize the partitioning of the graph in order to have nodes that have lots of interactions with each other together in the same partition. And then each worker machine is assigned one or multiple partitions by the coordinator node, which tries to optimize the assignment from workers to partitions. The system also has some support for fault tolerance, which is extremely important if you have a large cluster of many machines. If you have that and let them compute for a while, then it is almost guaranteed that at least some of those workers will fail, and then you have to be able to deal with it, ideally without restarting the whole computation from scratch. The Pregel system achieves that by a checkpointing, which means that worker nodes, they persist their inputs and their internal state at the start of each iteration. The coordinator node detects worker failures by pinging them regularly. And if failed workers are detected, then we start a recovery, which means that we might have to rewind a couple of super steps, and we repartition the partitions of the graph that had been assigned to those failed workers. So here we have to redo perhaps a couple of iterations depending on what checkpoints are available. They also describe a more refined recovery mechanism in the paper, which they call confined recovery. Here the idea is basically that the workers log even more data, and that allows us to restrict the recovery efforts only to those parts of the graph that were assigned to workers that failed. So here we log a little bit more, and therefore we would have to do less work at a recovery time. The way you would represent PageRank in Pregel, at least a simplified version, is what you see here. We essentially have to implement the compute function that will be invoked for each node and each iteration. Here, the incoming messages correspond to packages of a PageRank value. This is the variable marked in blue here, received PageRank. And in the first step in the computation, we want to calculate our new PageRank value by summing up all the received PageRank values. Then, in the next step, we iterate over all the outgoing links, and we are sending an equal share of our new PageRank value to those outgoing links. And in the next iteration, those messages will be received by the target nodes, and they will calculate the new PageRank values based on that. So this code is a little bit simplified because we don't explicitly consider random jumps or how we handle dead ends, meaning websites from which we have no outgoing links, but this is the principle. There's a couple of optimizations that you can do. For instance, you might feel that now we are actually sending a lot of values around in each iteration. Pregel has some mechanisms to reduce that. There's, for instance, a mechanism called combiners, which allow you to define functions to combine multiple messages together into one. And that can significantly speed up the process. I believe in the paper, they mentioned speed ups of up to factor 4. All right, so this is one example for a system that does graph processing at an extremely large scale. So now we have seen two systems, new for J and Pregel, both for processing graphs. We are currently generally looking at different types of data beyond relational data. So in the next lecture, we're going to start with a new type of data, which is data streams. All right. So I think we won't start with the new topic anymore. If there's any more questions, then please feel free to ask them in the chat now. And gonna give it a few seconds to see whether there's more questions. All right, I believe there's no more questions on graph data processing. All right, in that case, have a nice day, and then I see you again on Friday.